Okay, good afternoon, everyone. It's a pleasure to welcome our today's guest for the colloquium. It's Professor Gerhard Wurm from University of Duisburg-Essen. And he sent me his short CV and some research highlights. So I will just go through them to introduce him. And well, I'm really interested in the topic because while reading through that, I found out that we have a lot of things, a lot of interest in common. So I'm really looking forward to this presentation, but let's go into details. He studied his diploma physics at the University of Aachen and made his PhD at the University of Jena. In between, he was research associate at Max Planck Institute in Jena as well, and also the University of Jena. Then he changed to the US for a couple of years, well, 1 year actually, to the University of Colorado in Boulder. And he came back to be the head of the Emmy Neumer Research Group at the University of Münster. And from 2007 onwards, he also was a Heisenberg Fellowship in Münster. And since 2009, he's a full professor for experimental physics at the University of Duisburg. And so his research interests were mostly to do with sand and grains, predominantly in protoplanetary disks. So that was his main interest since his PhD. And in between, he was also interested in, let's say, saltation of dust grains in the Martian surface, which is somehow a bit common to charging particles in protoplanetary disk because charged particles behave differently than neutral particles. And so there's a really interesting field. And also noticed from his highlights that at some point we had a really nice interaction because he was referring to works we did years ago on a solid state greenhouse effect. So there's another overlap of our research interests. And lately he was dealing mostly with collisional charging and potential implications for planetary formation. And most of this work is fitting for experimental physicists was in drop towers, so it means in low gravity environments, parabolic flights and such things. So I'm really looking forward to this presentation, and the floor is yours, please.
Yeah, thanks, Günther, for this nice, kind introduction. And thanks, Peter, for inviting me. I always like to talk about the things we do. So let me share my screen. So I hope you can see.
Yeah, it's perfect. It's good.
Okay, so today I will talk mostly about charging, tribocharging of grains and what this has to do with planet formation. So I will introduce some problems, what I think are problems on the way to form planets and how tribocharging might solve them. Below there are a number of names. I certainly don't do this all by myself, but a lot of people contributed to this. So let me just dive into this. Just to set the stage, I have some planetary bodies of the solar system. The first one here is Jupiter's moon Europa, which is covered by water ice. And water is often considered to be important in the context of tribocharging. So certainly if we talk about planets, planet formation, this ingredient is there. We certainly have beautiful Earth, I would say a silicate planet, or at least if we talk about planet formation, silicates are often encountered and we do experiments with them in the lab. So that is also something that is important for charging what material you use. And just as one example for a giant planet, Jupiter here, which has a lot of gas. And if we think about lightning and all this stuff, gas is also important in the context of charging. So this is just to set the stage that we talk about planets and planet formation, that most of the ingredients you need for charging to be important are there. Okay, what I want to talk about is the formation. So just let me set the stage there. What we need, for example, know from meteorites and dating the sun is that they are both almost the same age. So it's probably good to look in some regions where stars are formed. And this has been done a lot with the Hubble Space Telescope. Certainly the new era is almost there with the James Webb. really looking forward to nice images there. Any case, I'm just picking one of the old Hubble images of the star-forming regions. You already see here that there's obviously a lot of radiation and ionizing radiation around, which has nothing to do with tribal. This is a different story. In any way, if you look a bit closer in these regions, what you see are these protoplanetary disks, which are on the order of the size scale of the solar system, sometimes a bit larger, sometimes smaller. There's another one here. These are still from Hubble, so they are 20 years old. I did not pick one of the nice ALMA images, but another one from ground, actually here from the SEER instrument at VLT, showing much details of protoplanetary disks that you are able to see these days. So I'm certainly not an astronomer, and this is just to show what we are up to observe in these disks and know something about this. However, if you boil this down, what we have is protoplanetary disk, which consists of, let's say, 99% of mass of gas in mass, and 1% is dust. And from this, we want to make planets. And I like this figure, especially since you have already these charging things in here. But in the end, it's just a disk, and we have dust particles within, and we want to grow from these dust particles. So if we forget about charging for a second and just kind of introduce the problem I would like to solve, what we have in there are particles which initially are probably on the order of micrometer, submicrometer to start with. And there's nothing you can really avoid that these particles collide. Let it be Brownian motion initially sedimentation to the disk midplane, turbulence later on. You have relative velocity, these things collide, and if dust particles collide, they tend to stick to each other and aggregate. So if you continue on this way, or if you do a scheme on this, this one I took from a paper by Kreit. Top left, you start with some monomer, and initially you have a very fluffy growth phase, fractal growth. Fractal is a big word here that's not really very important in this context yet. However, if you grow larger and your kinetic energy increases, then your particles not just hit and stick, but you can restructure these things. The aggregates get more compact, and eventually you end up with something which is called pebbles here, which is pretty compact, let's say 30–40% of filling factor. And then you start no longer sticking these things, but rather bouncing. So that's the scheme for the early phases of planet formation. So starting from micron-sized grads, fractal growth to more compact millimeter-sized things later. So millimeter is probably a size I would put to these compact aggregates. Okay, this is the first part on the evolution towards planets, I would say. And this is a sketch I took from a review I wrote with Jens Theiser last year. And the first phase is kind of undisputed, I would say. However, if you then continue, you encounter, let's say, one or two barriers. The fragmentation barrier you find often in papers on collisional growth because the energy is then so large that you destroy things again, you stop growing. But there's another one before, which is the bouncing barrier. Point here is that once your particles are compact, you no longer have this restructuring channel to dissipate your energy, and your collisions get more elastic. Just to show this, here's a movie from an experiment we did in the laboratory. This is a levitation experiment. These are just 1 millimeter dust aggregates levitating, so it's a 2D setup, if you like so. This marked particles are connected for a certain while, so they stick. However, these connections are not very strong, and the next collisions can easily destroy this again. So this is kind of what is meant with bouncing barrier. So you no longer kind of continue growing things once they are millimeter size. These aggregates were prepared beforehand, but if you start just with dust particles, it is set up. you grow things and you also end up with something on a millimeter size scale, which then only collides but no longer grows further. So that is the first point to make, that the bouncing barrier in planet formation is really robust. If you self-consistently just collide things, dust will not grow larger than sand. Okay, sand for me again means millimeter. So that is always something I'm talking about if I'm talking about these collisions in this talk. There's another evidence that millimeter might be a special size scale that comes from meteorite research. So this is just a slide through a meteorite named Allende. That's one I bought 2 years ago or so for some different research that was more on sticking properties of meteorite material. Anyway, what you see in there are these millimeter-sized objects, world famous, known as chondrules. And just kind of getting back to the topic of charging, one mechanism how they might have been formed is if they were dust aggregates before, which have been flash molten, maybe by lightning, and then cooled rapidly again, then you end up with these millimeter particles. So two things. One thing is, obviously, it would be good if a lot of particles would be kind of stuck at the bouncing barrier, being millimeter size, to transform them to chondrules then. And the other is that charging might have its say in this. Certainly, if you talk to meteoriticists, I'm not sure lightning would be their favorite model for this. There are other mechanisms to do this, like shock waves, shocks, these things, but that's not the detail here. Anyway, let's assume we could grow beyond this millimeter size. So if you grow to centimeter or decimeter, then different mechanisms kick in. This is just an example movie taken from Jake Simon's website. So if you put this in the disk and do some hydro simulations, these particles can kind of concentrate in larger clumps and eventually might become gravitationally unstable. So you need centimeter to decimeter particles to do this. The idea behind this, if I would say it from an experimental point of view, is they behave like a peloton. The particles just kind of join other particles and move along in the wind shadow. I know it's more complicated, but I think that is an image I can get, and I think it's not too wrong. So any case, so on the left, we know we can grow to sand-sized particles. And if I say sand, that is still a dust aggregate. So it's just the size is sand size. And once we would have pebbles, also here, pebbles in astrophysics is used very carelessly. So astrophysicists don't mean pebble really to be a stone as shown here, but it's again, a dust aggregate, and some people even think meter-sized objects, they call them pebbles. So for me, it's sand millimeter size, and the pebbles are more like centimeter, decimeter sized objects. And we can grow the sand, and we can grow from pebbles, but there is 1 or 2 orders of magnitude in between we cannot explain yet. So here's the pre-tribocharge situation, I would say. You have this disk, little charge in the center, dead zone, whatever, so it's pretty uncharged, and particles only grow up to the bouncing barrier. Now we did an experiment some couple of years ago, 2015 or so, and Günther already told you that we were doing some solid state greenhouse whatever effects. So we had an experiment, nothing to do with charge, in a drop tower, where we studied thermal creep through a dust sample. So on the right is an illuminated dust bed, if you like so, and we wanted to trace this flow. So we had some particles here on a piezo actuator, and if I let this run under microgravity, you see the particles flow to the left, they trace the flow. But you also see that at the bottom here, a lot of particles just bounce and return to the actuator. And if you're on the ground, that would be nothing special, but this is under microgravity. So why do the particles return? And it is because they charged. And I never thought about this before, but these were all identical grains. I was thinking, well, if identical grains charge, that looks kind of interesting. So the situation then was, well, we see these grains charge when they bounce. The same time, we were looking for something beyond this bouncing barrier. And we have this idea that charging lightning might have been proposed for chondrule formation. So maybe this collisional charging can solve some problem here. Okay, then you kind of look into the literature about tribocharging, and we know material difference is often the first thing that comes to mind. We all know this from physics classes on electrostatics. If you rub something on something else, both things charge, positive, negative, you have this tribose electric series then. But that's a pretty common thing. But if I'm talking about planet formation, let's say silicates, all the same material, essentially all the same size, that might not be important. Next thing that comes to mind is that you frequently consider or hear about charging if the particles have different sizes. So I took an image here from Vaitukaitis et al. 2014, 2 different sized spheres. The small ones become negative, the large ones positive. That's the typical thing with these particles. So that is something to keep in mind, certainly with charge separation due to size separation and lightning. And I like this, actually these lightning experiments by Cimarelli in the laboratory. We once thought about doing this by our own, but I thought that would be quite a mess. So we refrained from doing this so far. That's certainly something to keep in mind, but I still don't think that is something for the bouncing barrier. So that only came up when I thought about if you really would take identical grains where there is no bias in a symmetry breaking thing or so that you would expect one particle to charge one way and the other differently, do they really charge, or would they charge, or do they not charge? And at these times when we did these experiments on thermal creep, I got to know Troy Shinbrod, and he was exactly working on this charging of identical colliding grains. And I could kind of contribute with our experiments to one of his works there. And then I thought this is something to continue, because if we really now can charge identical grains, then probably we can turn this bouncing ensemble in something like a grain plasma. So with negative and positive particles, even if they're the same size, same material, overall neutral, which is important. I come to this in a second, and grow larger. So that is when we started to doing systematic experiments. This are funded by the DLR or BMWK. They always need acronyms for projects. So we decided the first one was Lannister. That was kind of Game of Thrones times. Meantime, this changed to Stark. Probably we have to change our names since Game of Thrones is no longer topic. Anyway, just stupid things you do while you're doing research. The experiments we did in the drop tower, from the idea here, pretty simple. You have a container with a sample, you shake it, and then you inject the particles into a chamber with windows. You can observe this, and the walls are capacitors so that you can trace electric charges. So if you look, and this looks following. So from right, the particles are injected, and you see positive particles move upwards to the negative capacitor plate, and the negatives down. And this way we can determine net charges, especially since our particles are perfectly identical. We know the mass and all these things. Okay, first things to note is, do they charge? Obviously they do. You saw these trajectories, and you can do a charge distribution. And this is what we find. This looks pretty symmetric. So it's centered around 0. The whole cloud is essentially neutral. And you can charge these particles. There are sub-millimeter glass spheres up to 10 to the 7 elementary charges. Why is cloud neutrality important in this context? This has to do with the fact that if you need it for lightning, it's probably okay if you don't have it neutral, because you have charge separation. You want these large electric fields. For breakdown, not sure you want it, but you get it anyway. However, if you would all your particles be positive or negative, that would kind of induce some barrier, because due to Coulomb repulsion, aggregates might at a certain stage no longer grow. This, for example, has been discussed in some work by Okuzumi, that especially at the surface where you have this ionizing radiation, you have some kind of plasma, the electrons like to stick to the grains better, they all charge negatively, and that would prevent at some stage that you get further growth. If you would kind of be able to mix this to the midplane, you also would have this charged aggregates, all of the same polarity there, and that might prevent further growth. That's known as charging barrier. I'm not sure that it's really so efficient, but anyway, that's out there. Now the contrast, if you would have particles which have opposite polarities, then you could grow something like ionic crystals, just like salt crystals. So just alternating positive and negative charges, you could make some aggregate or cluster of these dust aggregates, which is very stable, but overall neutral. And that's, I think, important for the growth. Okay, so what do the experiments tell us about this aggregation in the experiments? First, we start with individual collisions. This is from a group from Heinrich Jäger's group in Chicago. They have their own, let's say, homemade drop tower with a second or so microgravity. And you see particles on the left, obviously attracting each other due to electrostatic forces. You see a bigger aggregate forming on the right. And we did similar experiment in the drop tower, but we have about 9 seconds in Bremen. So on the top left, you see two particles colliding several times. And even if they kind of separate several particle distances, they find themselves again and again, rebound, lose some energy, eventually they stick. On the right, you can continue with this with a dimer. There will be another dimer coming from the bottom in a second. That's here, yep. And they collide, unfortunately, behind this other aggregate, but then they emerge as an aggregate consisting of 4. And you can continue this game of kind of following up to smaller clusters for a while. So here just snapshots. You start with a cloud with individual particles and end up with aggregates consisting of about 10 on the order of particles. Okay, how far can we play this game? Can we grow bigger? Because that's eventually the point, growing from this millimeter to decimeter or something like that, centimeter at least. So here's another experiment. We're actually currently trying to we're building an experiment for a sounding rocket so that we have more time to observe than it's 9 seconds in the drop tower. However, we could already grow something in the drop tower in a slightly different setup. So here are, again, a few cells, a couple of centimeters in size. They're slowly vibrated during the microgravity time to induce more collisions. But the important point here is how we prepared our samples. So it's all sub-millimeter basalt spheres. So the sample is the same. It's just that on the left, the particles were not shaken before they were injected in this chamber, but they were kind of left standing alone. That for us kind of implies that they are not charged. After a few years of charge measurements, I'm pretty careful of calling something uncharged. You can almost never avoid charges anywhere. However, they're probably not as charged as in the other cases, which were vibrated. And in this case, you don't really, on the left, you don't really form larger aggregates, while on the right cases, the middle is in 1 bar atmosphere, the right more in vacuum. You create very large aggregates, especially the one on the right. I think it looks like a bet, but if you don't like bad jokes, the science behind this is that all grains in this chamber are essentially collected in one big aggregate, and you can only do this with charged particles. But if we can do this in a protoplanetary disk, that will solve the problem because we are kind of growing from millimeter to decimeter size. Okay, so that potentially solves one of the problems in planetary formation. namely that we have the bouncing barrier. We have this streaming instability stuff coming later by these hydrodynamics. In between, you have 1 or 2 orders missing in size. And these big aggregates might kind of grow if you consider tribocharging in this. Okay, we're currently on the way to do longer time microgravity experiments. We also did the first experiment on the space station. That was actually a student experiment when our German ESA astronaut was on board. The experiment didn't provide us with much new data. I liked it anyway. It's cool to have something on the space station, I think. The funny thing is that we sometimes do parabolic flight experiments. And on one of these occasions, Alexander Gerst showed up there. Now we do this frequently, and I still like these flights, but if you write home that, well, we're doing parabolic flights, then everybody's saying, yeah, you do this so often. But if you say, well, the astronaut is here, then, oh, take a picture. So that's when I took a picture. And as you note, we are very kind of, you see that the flight was very strenuous for us, but he looks all smiling, so he's a very professional astronaut. Anyway, I'm not sure that with the fame transfer works out. Okay, that was just something, has nothing to do with science, but is just fun of research. So what are the limits? What are the largest clusters we can grow with charges? So that is a question of stability, and we probably cannot grow them all self-consistently, but then we have to turn to individual collisions again. So here's just an example we are working on currently, and this is a drop tower experiment again, where one of these big aggregates kind of collides with a wall. Just once again, I don't have detailed numbers on this. This is just to tell you that this aggregate, which shouldn't even be there without charge, is pretty stable in these collisions. It should kind of dissolve instantly otherwise. So that is something we currently work on. We also work on this in a more systematic way. Drop tower experiments are okay, but sometimes we would like to have more access to free particles in the laboratory. So we recently turned to levitate particles by acoustic levitation. So here's an acoustic trap, just a couple of transducers generating a standing wave. And you see some glass particles in the center, 2 millimeters. They are caught in different points of this standing wave so that you can capture some particles. What you can do with these, you can also kind of initiate a rotation. And if they rotate, centrifugal forces can kind of eject particles. And if you do this with charged particles, our idea currently is to analyze how stable charging makes these aggregates. Just another example with smaller glass beads, 90 micrometer, but a bigger aggregate. So if you follow this for a while, this kind of becomes unstable after a while and sheds a lot of its particle. That was just a test to see if we can do this. The challenge now is to make this more systematic and consider what charging does to this. Okay, that brings me to the next point, charging. We have to measure charge on these grains then, and the typical way you do this, I would say there are 2 classicals. One is you put your particles in a Faraday cup and it gives you a net charge. As you saw with our drop tower experiment, we can also analyze trajectories in an electric field that gives us the net charge. But is the net charge really enough to study all these problems we have at hand? Because if you collide particles, it might not be homogeneously distributed on your particles, but you might rather end up with a really patchy surface, like having negative patches, positive ones, and even if the total particle is, I don't know, 10 to the 7 positive charges, you might still have a very complex surface. And that might make all the difference in the world. Let's start to look at this again with the drop tower experiment. So in some cases, we have these aggregates, they have some net charge. So they're attracted to an electrode and collide with this very rapidly. and then it disintegrates, and you get the trajectories of all the components, and that gives you the net charge of the components. And if you do reconstruct your aggregate afterwards, there are some negative, positives kind of connected. This would be kind of probably in agreement with one of these ionic aggregates. That would be okay. But what we also found there are aggregates which only consisted of positively net charged particles. And that is something which makes you think, why is that possible? So one way to do this is that if one has a lot of positive charges, you can have induced dipoles and still be kind of stronger in attraction than repulsion. That is some work done by Nuno Araújo, for example, on these things a couple of years ago. Okay, the next level though is that you might consider that the particles are not really homogeneously, but you might kind of simulate the particle charge as being offset the center. We also did analyze this from the drop tower experiment. So let me guide you through this one, which is otherwise probably a bit crowded. So again, we have these simple drop tower experiments. We have rebounding particles, rebounding from an electrode, and we have sticking ones. And that's just in these trajectories. You can observe if a particle is rebounding or not. And what that means, if you kind of analyze this depending on the velocity, you find something like a sticking velocity. That's a typical thing you find whenever you do collision experiments. Usually for uncharged grains in the millimeter range, that would be millimeter per second or sub-millimeter per second. But our particles kind of succeed to grow up to decimeters per second. So that's really already again stability. But how is that possible? Because if you would have a particle kind of approaching another one on the wall and you have some kind of a mirror charge there, you might speed up, but if you don't lose any energy, you will just rebound again and not stick. However, there's always some small amount of energy dissipated. Can describe this by a coefficient of restitution. And if your charge is offset, then you get a higher boost in collision velocity closer to the surface than if your particle offset would be, for example, on the other side. And then you lose some energy, and the absolute amount is stronger in this case than in this case. And that allows you to stick to the surface afterwards. So this is, for example, something we can explain with an offset charge. Anyways, that's already enough to explain all we observe. Another fact we get from these drop tower experiments, again, same kind of experiment. Let's see, you have two particles which move around and sometimes they meet. So they collide and stick together. And we can determine the charge before, so we know which charge is on each of these particles. And afterwards, they kind of make an electric dipole, and this is oscillating in the electric field, so you can measure the oscillation, and that initially gives you the electric dipole moment. And if you measure this, the black dots here are our measurements, but even if you place the net charges which we measured on the extreme ends of your particles, that's the blue line here, it cannot explain the dipole moment we measure. And even induced dipoles, which would not be an issue for a spherical particle which is symmetric, but for this dimer it would. If you estimate this or calculate it, it's way below what we measured. So the only way you can explain this, or at least one way you can explain this, if you have this charge patched model, then you end up with possibilities that are in the range we measure. Okay, so that is something which is promising, but again, in drop tower experiments, it's only 9 seconds. Eventually your particles or dimer collides with the wall, and you cannot follow this for a longer time. That is on our list because we want to know how these changes, let's say for hours or days or so. So we started to do this again in our acoustic trap. First measurements with an electric field show that we can have these oscillations there as well. And here's just some first test measurements on the dipole moment of small aggregates up to 7 individual particles with charged and not charged, uncharged cases. And that is something we are currently working on. Okay, who cares about all these details beyond net charge? I told you that this might make all the difference in the world. If you see this charge distribution and you note that here is a logarithmic scale, then most of the particles are actually neutral. However, if you consider that you have this complex charged surface, that doesn't mean it's unimportant for aggregation, because you only need 2 spots of different polarity close by on a surface and you can increase your sticking. Sorry. Okay, so that kind of leads me to the next topic, and that is zero charge, discharge. What does zero really mean? And here are some thoughts about this. The first thing is, I already told you, net charge is different from this complex behavior. But would you call one of these complex spheres, which has a net charge of 0, discharged? Or does it have to be homogeneously discharged? And a lot of people who work in a laboratory, if they want to charge or discharge their particles, they kind of use ion sources, electron sources, whatever. And if you kind of do this, what do you do with your grains? Do you really kind of neutralize them, like an ion shows up, picks up some charge from the surface and leaves again? Or is it more like in the bottom part, if you have these aggregates, these particles with some charge patches, you just add new patches on top and kind of masks the charge below? Because that's different. If you like bad comparison, that's like if you want to put on a new wallpaper, do you peel off the old one first or not? Because if you don't, everything that has been there is still there, and you might probably use it later on. So your charges, your charge carriers would still be there. Anyway, so what's important in this context is the time scale of charge redistribution. For example, if you have some patches initially, would they all count in an electric field? The positives move upwards and the negative downwards. Would they discharge on timescales of weeks or so? That's important for protoplanetary disks, because 2 millimeter particles might only encounter each other once a week or so. And here are some thoughts on this as well. So same experiment, but now different way to look at it. We again have our rebounding collisions at the electrodes. And if I have a positive particle impacting a negative electrode, my naive thinking earlier would have been that if you do this, they kind of discharge at the electrode. But that is not what we see, because what we see is here, if the positive particles here, positive charge, that's the charge on the bottom axis, if they hit the negative electrodes, the charge transfer goes in both directions. So they can even become more positive afterwards, same on the other electrodes. However, if you look at the sticking particles, we can eject them again by kind of kicking the experiment a bit. And if you do this, that looks more like the expectation. So the ones at the negative electrode become more negative, and on the positive, more positive. And our idea how this works is that we probably, well, I like the idea that water ions are the charge carriers. So we probably have our electrodes. If we have an electric field, there will be some charge separation in the top mono layers of water on the surface. And if you connect this with the particle surface then, and you only do this in rebound, the idea would be that a millisecond or smaller than a millisecond would not be enough to kind of separate the charges. And in the end, you just separate the particles, but what is kind of transferred depends on what was on the particles. So either the positives or negatives can just be kind of ripped off. So essentially always the particle loses some charge. And if you have something longer than a second or so, you might rather have a separation of the charges. And if you rip the particles apart then you might kind of have this systematic way due to the electric field. Anyway, that is just our current model on this, and there's probably more room for this. So on a small time scales of minutes or so, I don't think that this will happen, this restructuring on the surface. But as I said, that might be important in the future. We already started to do some long duration discharge experiments. So we charged some glass with some tissue, just some tribocharging, and have this in a vacuum chamber and occasionally put it in a Faraday cup. And we do this even up to a couple of weeks. So what we find here that if you do this, for example, at a pressure of 1 Pascal, so similar to Protoplanetary Disk, 1 AU, the half times here is more like a month. So particles don't easily discharge at low vacuum. That brings me to the let's say last topic here, the discharge at different pressures. So what role has the gas phase in this whole business? We already know that there are things like lightning. Can we do this in a bit more detail? Since we have these different pressures in a protoplanetary disk, we once started to measure the charge on grains. Again, you vibrate something, measure it in a Faraday cup. So now it's again just net charges. And we noticed that if you do this at millibar pressure, the maximum amount of charge you have on these particles is limited. And that's fairly in agreement to some Paschen curves. So indicating that you have some discharges here, but this is kind of limited to sub-millimeter pressure in these earlier times. Might be applicable to Martian atmosphere, different story. But what we also did is set up a high vacuum setup that needs more care, but we did this. And then we find that even down to 10 to the minus 8 millibar, you still get charging of the particles. But it kind of gets to some equilibrium, and that's also kind of in agreement to discharge theory if you do this breakdown voltage business. Just note that if you do this breakdown, you typically apply some voltage between some electrodes. We don't have a voltage here, but we measure charge or charge variance. There's another single point here, that is that when at very low pressure, we heat the particles and the whole setup. Beyond 100 degrees, we lose discharging. This is probably the indication, or one more indication for me, that water is a carrier here. That doesn't mean that high temperatures are bad for this. And I noticed that Christiane, for example, was also a co-author of some work on high temperature charging. So even at a few hundred degrees, you can still charging. But then water would still be present there, I would say. So it doesn't mean that high temperatures are bad in general for charging. Okay, is there more evidence? Now these were just charging measurements, some indirect things. Typically, if you have some discharge, might be connected to some visual observations, some light. In fact, we see this. So we did this experiment. Actually, I wanted to observe a single particle that did not work out to see it glowing. But if you have a vibrating setup with particles in it, and if you put this at low pressure, millibar pressure, and kind of observe this for a minute or so with the camera, you see a faint glow surrounding your setup. So at the inside where the grains are, but in this case, even on the outside, even though the whole thing is an isolated box. So obviously there are fields strong enough emerging from this experiment and having a glow on the outside. Now this brings me to the point that probably you have breakdown, discharge, and you have some ions going away from your patches or so. And this might actually mean that your charge transfer in tribocharging is not only constrained to your two particles, but your gas might play a role in this. So probably there's also in just simple collisions of two grains, some charge transfer to the gas. And we also see this in the drop tower experiments. So these experiments are very, well, they have various applications. So you see this in the inset on the top two particles again colliding, now rebounding, and we can determine the charges before and afterwards. And if you do the total charge before, that's on the x-axis, and afterwards on the y-axis, what we measure is these things which do not quite fall on the charge conservation black line, which is just the center line there. And that means that obviously some charge gets lost, and this is likely injected into the gas phase. So tribocharging also ionizes the gas phase in this environment. And that brings me back to this picture of protoplanetary disks. Obviously, this dead zone where all these collisions happen, because there is where this dense solid cloud is, might not be quite as dark anymore. There is collisional charging in there, and that might kind of charge the midplane of this disk. That is also something we just work on. That's not very elaborated yet, otherwise just an idea. Okay, I thought last topic, but maybe just 2-3 more transparencies on another topic that was so far more for planet formation, but once you're in this business of colliding grains or so, and Mars and all this, what naturally comes to mind that a lot of planetary surfaces, and you don't have to see the movie Dune, but since there's a little vegetation on other planets, a lot of them are covered by dust. And you have migration of dunes and all this stuff, and charging might play its role there. For example, if you look at Mars, there are dunes which are actually very actively moving, so there's motion there. If you take the pictures of the Martian rover and just kind of put them in between these ones here from Monument Valley, which I took myself some years ago, it looks like Mars and Earth are the same. And there are movies, another movie, that's The Martian, where they have this intense dust storm, which kind of suggests that the physics is the same on Mars than on Earth. However, on Mars, it's only a few millibars, and that is where the movie is wrong, because at a few millibars, pretty hard to pick up particles. It's actually a challenge. So charging might probably help there, or kind of support this. And we did a lot of, as Günther mentioned, experiments on wind-driven material, or we still do this. So we observe under what conditions particles are removed by wind. And we recently also started to do this with some charged samples. So again, vibrating particles, which charges the bed and then having a wind flow. And that is essentially my last slide here, that what you can do is determine the velocity of the grains depending on height. That gives you a friction velocity, some efficient wind velocity, if you like. And if you do this with charged grains, you see that the slope here is flatter than for the uncharged case. So that means that indeed you can pick up charged grains much easier. I'm not explaining this anymore, but that might be something to follow up. So charges might also have their share there. And once you're on the surface of such planets, and if you know that, for example, on Earth, these electric fields and dust storms can be 100 kilovolts per meter, so it might also then again impact the aggregation, because, for example, for hollow spheres, we see a chains forming in intense electric fields, which we don't see otherwise, but that's also just an idea. So my conclusion is that tribocharging might be quite, I think it's interesting for planet formation. It might have some important implications, like in using kind of new growth phase. It might kind of ionize the dead zone, and it might ease wind erosion. And with this, I'm finished. And even though I don't see you, I thank you for turning in.
Yeah, thank you very much, Gerhard. This kind of applause is always a bit appalling in these Zoom times. Just imagine you have a rich applause in the big hall and you can bow, etc.
Yeah, I will buy one of these buttons later for creating your own applause.
Okay, so we have time for some questions. There was already quite some activity in the chat. So maybe Sunny, I wanted to ask you, can you maybe say something about Günther's question about the non-spherical grains? Can you repeat maybe his question or what you think?
Yeah, so I think what Günther wanted to ask is that we also work with glass beads related to gas flow in pore structure, but we have experienced that while the larger glass beads are really nicely spherical, below 250 micrometers, they get very sand-like, so very angular and irregularly shaped. And that's an issue for us because the packings are not homogeneous anymore. And I know you're doing like a different kind of science with them, but have you observed any effect like that where the shape of the grains has an influence on the charging or on the interaction in the collisions?
On the interaction, yes. I mean, in earlier times when we used micron particles, you can use the spheres or quartz, which is irregular. And as you say, that has an impact on your packing fractions you can get. So you cannot pack irregular particles as close as the spheres, I guess, at least not at the same pressure.
Exactly, yeah.
For the charging, meanwhile, we also use powders or aggregates really of dust grains, which are milled and which are pretty irregular. But they also charge. There might be differences in your contacts are smaller, but the effects are similar, I would say. But that's just first measurements, and I don't have, let's say, publishable data on this yet.
Okay, yeah. Thank you. I will pass this on to Günther.
Okay, you can also, of course, use the hand tool if you have a question. Christiane, you had some entries in the chat, something about size thresholds. I think Günther might have said that already, but so there were.
I didn't.
Okay.
So I was wondering how small the particles can be in order to apply your very beautiful results. So what I'm basically asking is, we are looking at cloud formation, right? So, and I'm always keen to see how we can use the experimental results for our understanding of cloud formation. But our cloud particles are, depending on where we are in the process, rather small, definitely below 1 micrometer. So do you have a thought on that maybe?
I mean, yeah, sure. Well, my colleagues in Jena in 2000 or so did some collision experiments with micrometer grains, and they also charged. It's I'm not sure the charge density really only scales with this surface area. That might be a good proxy, but certainly small particles also charge. The problem is always if you have only small collision velocities, then they rather stick to each other, and then you don't get charge separation afterwards. So it would not matter that much for the net charge on the grains probably. But otherwise, I think it's not, well, there are other limits certainly in the breakdown thresholds, which is size dependent, if you make it kind of a voltage on your grains. Not sure that would be bad for small grains. So I mean, this is a very general question. So I think the concepts would certainly also work for small particles, I would say.
But no one really has asked the question when the concepts actually break down with respect to the size, right? Because if you think about induced dipoles and charge distribution, heterogeneous charge distribution, well, it's just two, but a non-homogeneous charge distribution on the particles, at some point these ideas must break down. I guess my more direct question is, has there been some thinking on at which size, if there is a size barrier for this process to break down?
Not beyond what I just said, I think.
Okay, thank you.
So again, if you have a question, especially that maybe PhD students can use the hand tool. Meanwhile, I have a question about the nature of these charges on the grains. So I think you more and more showed us some evidence that this is not something movable. So it's rather patchy, and that there might be negative and positive regions at the same grain. I wonder, when we, for example, if you have two of them having now a connection, is it possible to roll these particles? Maybe this is something you could measure in order to find out in how far these charges are also movable, or are they really more like fixed to the particular place they are on the surface?
They certainly roll. I mean, you see this also in some experiments. If you have particles with some, let's say, some irregularity which you can follow. So you have rotation, and these things can roll over each other. For the aggregates, you see in electric fields that they kind of stretch, rearrange to find some energetic, better configurations. Mm-hmm. And certainly this will also all kind of influence the charge on the grains.
So do you think the charge is moving along with this rolling connection, or is it something you think is rather fixed on the grains and they just roll from island to island, so to say?
I think it rolls from island to island, maybe make some new islands. I don't think it's moving a lot, but that might depend on the water content, for example, you have in the whole thing. We also have some experiments which more conductive surfaces, I would say, where I would say that you can also kind of distribute your charges on short time scales, but that might all depend on your environment. For the particles and the especially with these strong dipole moments we measure, that is not something I think you can explain with moving charges. So in this cases, I would say it's fixed.
Okay, last question, I think, goes to Christiane. I don't see any other hands at the moment.
I don't want to snatch the time for someone else, but maybe we can discuss this later as well. I was intrigued, of course, by your faint glow experiments. Do you have an idea or possibility to measure the temperature? And I'm asking because we have an experiment running in St. Andrews where we also do discharges. And we want to model it with our kinetic chemistry. Obviously, one of the biggest questions to solve is, what temperature does the discharge have? And there is not an easy answer like, oh, you just do a spectral measurement, because you only can do a spectral measurement if you know what chemistry you are looking at. So I don't know, did you think about this? What temperature your gas would have?
No, I didn't. Intuitively, I would say it's just room temperature, because it's such a faint glow in our case that it's, I don't know.
The thing is, you must have quite some high electrons with a high kinetic energy, right?
Yes.
So and then the discussion starts, how to define a temperature actually. So is it the electron temperature? Is it the ensemble temperature? And follow up how to measure it.
Yeah, I don't know. I have never thought about this. So that was never on my mind. I always just thought it's cool that it's glowing.
It is cool, definitely.
Actually, it took us a while to find an explanation. And in this case here, for example, it's probably due to the different materials from the shaker and the particles. And it's kind of a triboelectric nano generator thing. But it still intrigued me that the electric fields on the outside are strong enough to induce this glow. But you're right. If you do this, the gas participating in this should have a different temperature, but I'm not sure how to measure this.
Okay. I would say it's now time for our break. So we would like to thank the speaker once more, and I stop the recording.